All right, so last time we ended up doing exponentials and we solved some problems. We're going to now be doing logs. Logs are basically the inverse of exponentials. What are they used for? Logs were invented to be able to write really large numbers and really small numbers in a condensed form and also be able to put them in a graph all together. So if I had some points that had decimals like 0.001 and the number 10,000, putting them on a plot on a Cartesian coordinate plane like this one would be brutal, okay? So the logarithm was invented. It's basically a coordinate plane, but it is in powers of 10. So instead of having each box be 1 unit, each box basically would represent a power of 10. So the first box would be 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4. Instead of having the integers themselves be the boxes, it's the powers that will be the powers of the 10 that will be each box. And suddenly you'll see this grow really fast or really small. You can look up coordinate planes for logarithms. You see that the graphing is not equally spaced. They start like really tiny lines, and as they go, they start getting separated a bit more. But anyway, we don't have to graph logarithm numbers per se. We will be doing logarithm graphs, but those are much easier if you follow the instructions. So logarithms, we're going to be converting logarithm into exponentials and exponentials into log forms. Now that's because we don't know how to work with logs yet. So we're going to make something unfamiliar into something familiar. All right. So before in exponentials in the previous two sections, when you had a base and a power and the answer, b is the base, x is the exponent, y is the argument. You're like, what happened here? Well, when you look at something that's in log form and you have these three letters, they change position. Okay, so what I do is I do a circle. I call it the circle of life, Hakuna Matata. And that really does it like this. I will be given a form that looks funny like this. I will circle the base, the little number at the bottom. Most likely it won't be a B, it'll be a number. But I circle that, I raise it to the opposite side of the equal sign. Listen to what I'm saying. I raise it to the opposite side of the equal sign. Raising in math means power. So I'm going to raise it to the opposite side. So that will be the power, and it's going to equal to this. Okay, it's going to equal to that. So you have your B. This is how this gets converted to that. So I have a B, raise it to the Y, equals the X. That's why over here, this is your base, this is the exponent, because when you convert it, it becomes the exponent. Okay? And then Y is the argument in here. All right. Did I write it funny? I wrote it according to this. All right. Okay, so here I have some problems in which I want you to convert from one form to the next. I'm going to write this in pencil so I can erase it later. So looking at this, the log form to the exponential is a much easier. So I'm going to do these two, and then I'm going to do these two over here. So A and C will go first. I circle the base. I raise it to the opposite side of the equal sign, and then I equal it to the argument. The argument is this. Yes, I messed this up. I need to erase this. This is not correct. The argument is in here, and what it's equal to is the Y. I knew something was off. I have to fix the notes. So the argument is the X. The exponent is the 1. Okay. All right, so when I do this circle, I again start with the base. The base is 2. I raise it to this power, 3, and then I complete the circle by bringing it back to the 8, and that 8 is the answer. And that is true. I know that 2 to the 3 is 8. So because 2 to the 3 is 8, that means it is correct. Let's do the next one. Circle the base. Raise it to the opposite side of the equal sign. I say to the opposite side because sometimes the equal sign is on the left. So I don't want to say raise it to the right because the equal sign might be on the left. Okay, so I raise it to this power and then that equals 5. So 5 to the 1 equals 5, and that is correct. Okay. All right, the other way around is a little bit harder, but I am going to take my eraser and erase these notations so I have space to work with. Okay, so how do we do this? We write log. I put a box here, a box here, and a box here. There are 3 boxes. Log of this box, the box equals a box. Okay, so if I were to do this circle, I should end up with this. If I were to take this base, raise it to this power, equal it to that, I should end up with this. So where do things belong? Right? So again, this would be the base. So what's the base here? The base is 1/2. I would then raise it to whatever power. It's being raised to a -4. And the answer is in this box. The answer is in the box next to the log. Let's try it again. The base goes down here. So the base is 3/4. I raise it to the 0 power, which is here. And the answer is 1. And that's how this would be set up. That's the easiest way to do it. So why do we need that? Because if we have something like this that we need to solve, I need to know how to convert something I don't know into something I do know. So I'm going to convert this log, these log forms, these 2 log forms into exponentials, which will help me solve by what I just had on 6.3. Sorry, 6.2. So I circle the base. I raise it to the opposite side of the equal sign. See how this time I had to go left? And that equals the piece next to the log. So this is 8 to the x equals 4. You use your skills from 6.2 in making these bases the same. I cannot make this 8 into bases of 8. Sorry, into bases of 4. That is not possible. 4 to no power gives me 8. You can say, well, 4 times 2. Yeah, but that's not a power. So you have to shrink it. Let's do bases of 2. So that's 2 to the 2. And this is 2 to the 3. Now that I have them at the same base, I can cancel, equal the powers. So, okay, so 2/3 is the answer. This is no calculator. Okay, so the next one, circle the base, raise it to the opposite power, equal to that. X to the 4th equals 16. In this case, I don't have the x in the power, so I don't have to do what I did in 6.2. I don't have to make the bases the same because the base here is x and the base here is 16. Can't do it. So what I would do is I would take the 4th root of x. 4th root of 16 should be 2. How do I know? I split up the 16. 2 times 8, 2 times 4, 2 times 2. For every 4 of the same kind, I take 1 copy out. That's how I get 2. Okay. Even though it's done in pencil, I hope you can see it clearly. I can erase it and reuse this again. Had a paper clip somewhere. Just got lost. Okay, here, common log and natural log. So again, I'm just doing bits and pieces. I'm not doing the entire lessons. So for that, please check the media on Pearson because this is what I'm going to focus on the test. For these, again, you should have or make copies or take a picture of this right here. This you can use on the exam. Those are rules that you're going to need. Common log is when you have a base of 10. When it's not visible, it would be a base of 10. When you see an ln, just like you do here, okay, ln is the base of e, log, notice log is the base of 10. Okay, that's going to be helpful later on. We will explain properties of logs. And this should be on this page on the electronic book, textbook. Here are some properties that you might want to know. Log base a of 1 is 0. Log base a of a base a to a power k, these cancel, giving you k. If you have a base of a to a power that's log of a, that also cancels, giving you a k. Then you have 3 rules, which is going to help us solve these logarithm functions. It's a product, a quotient, and the power. Those will be a little bit later on, but for right now, we will have to condense and expand. Okay. When it is condensed, they will look like this. Condensed means one single log with stuff multiplying, dividing, or taken to a power. When it is expanded, each term has to have its own log. Notice that. Okay. So the product rule says that when you have a single log of 2 things multiplying, you kind of distribute. This is not technically distributing, but you kind of distribute. I'm not going to say distribute. You attach. You attach a log to each piece separated by a plus. When you are working with multiplication, multiplication is consecutive addition. So if I do 2 times 3, it means add 2 3 times or add 3 2 times. So addition and multiplication go together. They are the same thing. Multiplication is an easier way to do addition. It works the same way with division. Okay, when you are dividing, you're basically trying to see how many times something fits in something else. So you're taking away however many times you can until you can't anymore. So quotient division is related to subtraction. When you have 2 things dividing, they will each attach a log, but you'll have a negative separating them. Make sure that this minus is only given to the pieces at the bottom in the denominator. The power rule, if you have a power with a log, you basically bring that down right before the log, and that has now expanded. Okay, so let's go ahead and expand these. I will use a separate sheet of paper. Make all these eraser marks. A log of 8x. Okay, and I want to expand. So according to the rule, let me move this up, bring this down. According to the rule, I see that 2 things are being multiplied. Therefore, the way I expand is I attach a log separated by a plus to each piece. Done. That is all I need to do. You can't solve it. You can't reduce it. You can't make it pretty. That's not what we're testing. What we're testing is for you to use the rules. The next one is log base 5 of the square root of 8, I believe, right? Yes. Okay. So again, you don't do anything with the bases. The bases just keep being attached. Actually, I should maybe put a little base here. Base. Whatever that is, you just keep copying. It doesn't affect what you're doing at all. Okay. So here, I'm like, well, there's nothing I can do. It's not multiplying 2 things. It's not multiplying. It's not dividing. It's weird, right? This would be the one. So that's the same thing as the log base 5 of 8 to the 1/2. And we've gone over this, right? Square roots are 1/2 powers. And that's where you get the power rule to then come down to be able to expand. So the answer to this is 1/2 log base 5 of 8. That's the answer to that one. Okay, let's try some more difficult ones. C, log x, y, z. Okay, the first thing in the more broad part is that 2 things are dividing. So I'm going to separate this as the log of the top minus the log of the bottom. Now this one's done. There's nothing else. But this one has 2 pieces multiplying. So this is the log of x minus log of y plus log of z. Now, make sure that you know that these are together. You then have to distribute a minus. So your final answer should look like log of y minus the log of z. Remember I told you when I gave you the property for the quotient that anything that is in the denominator will carry a sign that is negative to the left. The y was in the denominator. That term should have a negative. The z is also in the denominator, so that term should also have a negative. Okay. D is the last one. Log base a. See, it doesn't matter the base. Cube root of m squared. This will be a power because there's nothing multiplying, there's nothing dividing. So what we do is we make this into a power. So that's log base a of m to the power over root, and then you bring this down to the left. So that's 2/3 log of a of m. Done. You are done. Okay. Now we're going to go the other way around. I am going to then condense. So this is example 4. Condense. Log base 3 of x plus log base 3 of y minus log base 3 of 2. So I usually take two things at a time. These two have a plus, so I condense it down to a single log. And so what happens to these two is they multiply. Then I take the next two. This has a minus, so it's going to divide this into that with one single log, which is why it's called condense. You don't carry this negative anywhere. This negative just means it's this division sign that separates the numerator from the denominator. That is all. Okay. I'm going to do one more, and that way you guys can do the last one yourselves. There are 3 of these, and I'm only doing this one. Okay. When you are condensing, you are moving all the powers up. That's the first one you do, and then you are doing quotient or multiplication rule. This goes up, this goes up. So this is log of base a n to the 2 minus log base a n cubed. Now you have a minus. It's going to divide this into that. So log base a of m squared over n cubed. Done. Okay. There are 3. I've done 2. Try the last one. All right. The last thing that we will see for 6.3 is the change of base formula. And this is basically when you are asked to do something in the calculator, okay? You will have a log of 2 numbers and you're asked to find the answer or the decimal. You basically take the log of the numerator and divide it by the log of the denominator. So if you want to evaluate this in the calculator, let me show you how easy that is. You're going to put log of the big number, 17, close it, divided by the log of 5, close it. That's the answer. If you accidentally put log of 17 divided by log of 5, it might give you a different answer, as you could tell, because it did things in a different order. You didn't tell it where to stop, okay? Some students say log of 17 divided by 5. That is not correct either, okay? So the only correct answer is the log of 17 divided by the log of 5, which is 1.76. Let's try this last one over here. If it says ln, it's clear. It doesn't matter. You're just going to use a different button, but it's the same idea. So the ln of the big number, 0.1, close it, divided by ln of 2, close it, enter. Okay? Do not make your own order. There is an order to things. So it's important that you know what to do. All right, this ends 6.3. I am now going to do 6.4, which is graphing. And then we have solving and one word problem, which is very easy. Okay, again, I'm not doing tens of thousands of examples, but you can get the idea. All right, with these problems, what you want to know is how do I convert something I don't know to something I do know? Well, log functions are very difficult to like just do them by hand without knowing prior what it's leading to. So I can't finish the video. There's always some kind of weird noise that just throws me off. Log functions. So we're going to make a log function into an exponential function. Remember, we circle the base, we raise it to the opposite side, and we equal it to x. So that gives us b to the y equals x. When we put this in our calculator, we can't technically do it because our calculators have the y equals. They don't have x equals. So we're going to have to be smart about this and do it on our own. So when you have something like this that you have to graph, log of base of a half to the x, you pretend this is a y, you circle this, raise it to that power equal. So the exponential will be 1/2 to the y equals x. Okay. Ridiculous. All right, so that's what we're going to use to graph. So when you look at the domain and the range, it's going to be the inverse of what we had already in the exponential. In the exponential, you had all reals for the domain, and then you had a restriction on the range. Now they're going to be swapped because remember, inverses of each other means that for every x, you have a y. For every y, there's an x, and that means everything got inverted. So every dot gets inverted. Therefore, if you were trying to graph something like this, you would then still make this kind of chart, but instead of choosing the x's, you don't want to choose the x's. You don't want to be like, well, what gives me a 5? No. Hell no, that takes a long time. You're going to choose the y's. So you would choose -1, 0, 1. The same exact values that you chose previously for the x, you're going to now choose them for the y's. That way, all you have to do is take those values and put them in the top, which is the exponent, put them in the exponent, solve, and then get these numbers here, okay? So when you do that, you will then get a graph. It's not going to look exponential like before, and it's not going to look like decaying. It's going to look inverted, okay? The domain is going to be, in this case, it's going to be 0 to infinity, like that. And the range is going to be -infinity to +infinity because it's inverted from the exponential. So whatever the exponential was, swap everything, okay? You would swap the table, you would swap the domain and the range, and that's what it would be, okay? Basically, this is what it's saying is this is the inverse of if you have 1/2 to the x equals y. These two would be inverses of each other. Everything swaps. Okay? Yeah, because you have the x's and y's in a different position. All right. So this is what I have here. Okay, in conclusion. Instead of having a horizontal asymptote, now it's going to be a vertical asymptote because everything changes. The domain is now a certain number, that would be the h, whatever this is, to infinity, and your range will be -infinity to +infinity. So if I wanted to graph this, I already have the table, I already made it, so let's go ahead and do that. Let me copy it down. If this noise can just go away, that would be great. I have -1, 0, 1, and I have 1/2 to the y equals x. So when I plug in, because I'm right next to the parking lot, when I plug these numbers in, this is the -1, that's a 2, 1/2 to the 0 is 1, 1/2 to the 1 is a half. So when you graph these, let me show you what it looks like. Let me do a quick sketch. You can make it pretty and everything, use graph paper. But basically what ends up happening is, here's your x, here's your y. 2, -1 is here. 1, 0, and then half 1. So your graph is going to look like that. And my asymptote is going to be this. X equals my h, which turns out to be 0. X equals 0 is the y-axis. Y equals 0 is the x-axis. Okay? My domain and my range. Notice that it goes up and down forever. That's why it's negative infinity to positive infinity. The range is now what the domain used to be in the exponential, and the domain will be starting from 0 all the way to infinity. Okay? That's basically a quick sketch done very easily, very fast on 6.4. Okay? The last one we're going to use is basically a transformation. So we're going to be plotting this. Okay? This is example 2. F of x equals log base 3 of x minus 1. Okay? That has too many things. So I have asked for the parent graph, and that is f of x equals log base 3 of x. The parent graph is dropping the h and dropping the k. In this case, there is no k, so I'm going to put a 0, but that would be the parent graph. So what I'm going to use is this. I'm going to make this into the exponential form because it's hard to do. This is the same thing as y equals log base 3 of x. So when I make this into exponential form, I circle the base, raise it to the opposite power, bring it back. So this is 3 to the 1 equals x. And now I make a table. Okay, when I make a table, I can always choose -1, 0, 1, -1, 0, 1. Just make sure you know where you're plugging them in, the y or the x. In this case, you choose the one that's the power. So that's -1, 0, 1, and you do the math. So 3 to the -1, 1/3. 3 to the 0, 1. 3 to the 1, 3. And you would plot. If I were to plot this, that would be the exact graph for this. Remember, these two are the same. This graph is the same as that. However, this is moved. So at the end, you're going to move 1 unit right. Okay, 1 unit right. So now you plot. Let's make a really quick sketch. I'm not even using graph paper because it's so quick. 1/3 -1. 1, 0. 1, 2, 3, 1. This one's going to curve this one. So the log functions are either going to do this movement or they're going to go this way. Okay. So my asymptote is here. Okay. That is for this table, which is the parent graph. I have not moved. I should have done it in pencil. But all you're going to do is grab that and move it 1 to the right. So I am not going to do it for you. You will go ahead and do it yourself. I know you can. You're going to move everything 1 unit right. Okay. And that will be the final answer. That includes, as you can tell, look at the arrows, that includes the asymptote. So then the domain, once you move it and you're done moving it, it'll be 1 infinity, and then the range will be -infinity and plus infinity. The asymptote should be x equals 1. Once you move everything 1 to the right, everything should now match the green. Okay. Okay. I'll just give you a simple example. I don't want you to stress out about these graphs, but you will have one on the exam, that is for sure. Okay, we've got 3 more examples, and then we will finish the lesson with 6.4, and that is on inverse functions, exponentials, and log functions. Okay, so this one is just pure algebra. And that is basically how to find the inverse. So we are now going to do exactly the thing that we did in 6.2, I believe, 6.1, on how to find inverses. But now we're going to be working with logs and exponential. It's a little bit weird. It's a little bit tough, but we can do this. So f of x equals a log of 1/3 of x plus 1 minus 4. Now the media can probably describe it different, and they might explain different. I don't care what way you do it, as long as you show me the work. First things first, make f of x into the letter y. Next step, change the x's to y's and the y's to x's. Okay, next step, solve for this y. I cannot solve for this y if I have something adding or subtracting. So I am going to add a 4. I'm going to try to isolate this as much as possible. So I get x plus 4 equals a log base of 1/3 of y plus 1. At this point, I cannot do anything else. I cannot distribute the log. There's no way I can get it out. You do not apply the properties. What you do is you go from log form to exponential form. And that's how you find the inverse, because that will get rid of this log that we need to get rid of. So if I make this into exponential form, okay, that will mean I circle the base, raise it to this power, and that's going to be equal to y plus 1. And now to solve for y, I just subtract 1. So my answer should be 1/3 to the x plus 4 minus 1 equals a y, which you should write as f inverse of x. Oops, sorry, I didn't make the box long enough. Okay, this is a minus 1. That's how you make or find the inverse of a log. You basically get to the point where you can't do anything anymore and make the log into an exponential. When you are finding inverses, if you start off with a log, you should end up with an exponential. If you're given an exponential, you give a log. So watch the next one. B, f of x equals 2 to the x plus 3. Start off by making this the letter y. Next, x equals 2 to the y plus 3. Try to isolate this piece as much as possible. That means I have to subtract 3. That's x minus 3 equals 2 to the y. And I can't do anything anymore. I can't bring that down or do anything like that. There are a couple of ways. There are many ways that you can see this or solve this depending on what the media. I do it differently, but I'm going to use the properties of the logs and the exponents. So how do I make this into a log form? I do log of a box equals a box. Okay, if you look at these 3, there are 3 pieces, piece 1, piece 2, piece 3. Which one's the base with the exponent? The base is 2, so that goes here. That's going to be raised to the power, which is the y, and that's going to be equal to the answer of x minus 3. When I magically do that, log base 2 of x minus 3 equals y, I have magically solved the y. Okay? I've got one more to go, and I will end this lesson so it's not way too long. F of x equals negative e to the x minus 3. Okay, so let's check. Y equals negative e to the x minus 3. I then interchange. I try to isolate this as much as possible. So I add a 3. So I get negative e to the y equals x plus 3. Now, I don't really like this negative, so what I'm going to do is I'm going to divide by it. I'm allowed to because it's like an imaginary negative 1. So that's going to change this to negative x minus 3. And I don't care how ugly this looks. I just don't want to deal with negatives when I'm solving for y. And this is another one of those situations where I don't have a choice but to use my exponent form into my log form. Now this is an e. You can use ln instead because ln and e eventually cancel, but it's up to you. So let's use ln box equals box. The reason why I want to use ln is because if I put an e here, eventually I think I don't have to write it. It's like writing an x without a coefficient. So the base, here's a piece, here's an e, here's a y. The base is e. It's raised to the power y, and that equals negative x minus 3. So I have y equals ln of base e of negative x minus 3. Another way to write it, and don't forget to change this to f inverse of x, is not writing the e. If you put ln with just this, it's understood that the base is e. If you did not use ln, the natural log, then you would have to keep the e at the bottom. If you, let's say, used log, you would have to keep the e. But if it's ln, you could write it this way, or you can write it this way. Okay. And these are a bit rough, they are a bit tough, so please make sure that you have enough time to go through all of them and practice. Please, please, please practice. All right, I'm going to stop this video and I'm going to do the last 2 sections in the last video. So make sure you study.